presentation, let me speak about Vivoka at the beginning and our ecosystem so you can understand our background. Vivoka today is a young startup that has 7 years old, which is specialized in speech technologies. And today we are more than 30 employees, and 20 of them are in the R&D and deployment teams. Our products cover more than 60 languages and are deployed on more than 200K devices. But our start product is called VDK for Voice Development Kit, and which is an online and offline toolkit that works also in embedded device. It contains the main speech technologies typically needed to build voice assistants and customize them depending on the wanted use case. I mean, okay, so VDK contains mainly, let me say, wake-up word, text-to-speech, natural language understanding, and ASR components. Okay. So today, Vivoka collaborates with several industrial companies like Bouygues, Vuzix, Thales, and so on, but has also some technology partners like Siemens, Vanover, Sensory, NXP, and INRIA in France. So as you see, I would like to precise that in Vivoka we are not specialized in embedding systems, but we use them for deployment perspectives. So this presentation will contain a light overview of automatic speech recognition, what we call also ASR. Then I will discuss about an example of challenges that we meet while deploying ASRs on embedded devices. And I will also discuss about optimization techniques that we adopt to solve these challenges. In fact, ASR has been with us in the industry for a long time, in fact, for decades. However, only in the fast deploying in mass devices like Google Home, Alexa, Echo, and so on. And all of these devices use ISR, and these ISRs work with high. When you speak about accuracy, the measure that we use to evaluate the ISR accuracy is called word error rate, and it's a measure that gives estimation of errors in the transcription. So best ISRs have a lower word error rate. So ISR word error rate have been improved this last decade thanks to deep learning to achieve 3% of work for machines versus a mean of 5% for human. And all of these improvements were obtained thanks to deep learning. Today, ISR is mostly implemented in the cloud side. So if we take for example my phone, it's only acting as a recording and transmission device. I mean that the conversion of the acoustic signal to human speech and its processing also are done on the cloud side. And this has some issues. So first of all, we have the data privacy, and then we have some other especially latency also, and other issues like scalability or significant power consumption. So to go on depth on in speech, automatic speech recognition, we will see an overview of speech recognition, how we build ISRs. So to in the 70s, some researchers from IBM started to modelizing speech recognition as an information theory problem. So there is, in this case, as the figure illustrates, there's a word string W that the speaker has in mind. Let's say, I want to say this, and then the speaker box realizes this Bible pronunciates the speech A. And on the other hand, we have the answer box, which tries to invert the problem. I mean, for the answer side, the problem is if I solve A, can I find out an estimation of W? And from a theory affirmation point of view, we want to find W that maximizes the word sequence given the speech A, which is the first equation. But once we apply mathematical transitions, we obtain the second equation that contains two main components: the probability of A knowing W and the probability of the W. And these two probabilities correspond to the acoustic model and to the language model. So now let's take a look at the manual speech transcription process. Just want to understand how it works. So here we have an example of a dedicated tool. And for a given speech, the first step is listening to it. And in general, the transcriber uses this kind of tool also to observe the speech signal in order to split it and validate the spelling. Then, for every split, what we can also call a frame, transcribe the corresponding sound, which we call also a phoneme or a phone. And in this example, the first and the last frames are space, as you can see. The second one is the sound G. The third is I, and so on. So after this step, the transcriber splits the obtained phones in the third step here, and concatenates them and gives the most likely words corresponding to the phone tokens. Here, for example, which is the fourth step. But in the last step, so the transcriber will obtain a kind of sentence, and he will verify the grammar and the obtained sentence and check if it contains errors. So to summarize, the manual transcription could be or could contain a first step as listening, an observation step, a phone transcription, word transcription, and eventually a sentence reviewing step. On the other hand, we have the automatic speech recognition. And this one was also inspired by the manual process. And in a typical ASR, we find a first block which is feature extraction, which allows us to convert the signal from the speech from a signal to a vector to a numerical vector to allow the computer to process it. After that these features are provided to the acoustic model, which will give the sequence of phonemes, but without splitting them. After that, these sequence of phonemes will be given to the lexical model, and this one will split them by a kind of words. I mean words, but written by phonemes. And the last model, which is the language model, will translate or will convert the words written by phonemes on a sample readable sentence. So I have, okay, so only one thing that I have to precise that this is a classical or typical ASR, and At the beginning of this approach, all of these components, I mean feature extraction, acoustic model, and so on, work or used to work only with a statistical algorithm or a light machine learning models. So with the rise of deep learning, as we can see here, we check the number of how much time the terms machine learning and deep learning have appeared on the publication from 1997 2017, and we can notice the rise of machine learning. So we have in 2017 a 400 sites. But for deep learning, we can notice also the gap between 2016 and 2017. So after that, the deep learning started taking place on the ISR, and especially in acoustic model and language model. But the problem here in the every component acts with its own objective. And the pipeline tries to solve the ISR task locally, I mean in every component. So instead, the idea was, why do not use deep learning as a big model? I mean, let's train a big model that encompass all of those components together. And in this way, here we can, as we can see, we have the classical approach in green that will be replaced by a large neural network, and it will be our end. And as example, I'm not going to go in depth in this model, but it's only to show you how it works. So here we have the signal, the speech signal in blue, and we let the model do everything to obtain at the end our text. At our ISR, we have three main key or three key performance, especially for inference. We have accuracy latency, which we classify them as a pure performance measure. Also the footprint, which contains the computing and the storage, and the power consumption. And on the other hand, we have two configurations possible. We have the cloud devices and the or cloud configuration and the embedded devices. And as you can see, for the cloud, the most important measures are accuracy, latency, and computing. But for the storage for the computer consumption, it doesn't matter. However, for the embedded devices, all of these measures are important. So now let's see an example of the challenges that we meet when we deploy ISR on embedded devices. So let's take a classical architecture of ISR. So here we have the pre-processing components, and we will focus on acoustic model and the decoder model. So for the acoustic model, let's take as example a vanilla RNN model. This is typically this has typically an activation function or a state update function that we call H, and H typically is or contain 1,000 by 1 element. So here, sorry, I put it parameters, but it's element. That means that the function f takes as input two matrices. Each one has 1,000 by 1,000 parameters. So here we don't put all of these 2 million parameters in the local memory, but what we want to do is to put them in the system memory. And those are going to be pipelined through a local memory into the DNN for processing and chunks. And it's done in a pipeline fashion. If we assume 8 bytes for or bits for each one of those parameters, now we have 2 megabytes of data going in DNN. And if we assume that this RNN has to be updated at a rate of 100 hertz, then we have 200 megabytes per second streaming into this system. And in a modern state-of-the-art of ASR, you wouldn't see a vanilla RNN, but you would see something like LSTM, which are 4 or 5 times more complex than vanilla RNN. Okay. So now let's focus on the decoder side. And in fact, the decoder side contains the language model and all of the language stuff. So the way the decoder works is it generates a small phrases that tests against the language model and sends in an address through has a hash function, like we see. Then data is retrieved, sent to the decoder to update the probability of certain key phrase, and then finally we pick the phrase with the highest probability and give the text. So as you can see, for the acoustic DNN or deep neural network, we obtained a high computational complexity, but an acceptable storage and memory access. For the decoder part, we have a low computational complexity, but on the other hand, we have a high storage and memory access. So here we have some here we have some measurement of the performance of two ASRs for two configurations. The second one is the command recognition. So here we have we pronunciate a sentence and we check if the ASR output fit exactly our sentence. And for the simple utterances, we have many hypotheses provided by the ASR. And we test our ASR on 3 configurations. So as you can see, we have x86 and so on. And you can see that the RTF, which is a computational time divided by audio duration, could change between configurations. So for the arithmetic optimization of our ASR to be deployed on embedded devices, some of solutions that we use. One of the solutions that we use is called ONNX for Open Neural Network Exchange. And ONNX is a toolkit that allows a nice portability and interoperability also, and works on several platforms like Windows, Mac, Android, and so on. And it fits also with different architectures like x40, 64, 86, and so on. ONNX is also supported by several companies like Sony, Microsoft, and so on. And for the deployment stack, in fact, the pipeline starts with the front end. So if you want to build an ISR, so you have to build it at the beginning on your PyTorch side. Then you have an intermediate representation with ONNX. After that, you will need an ONNX runtime, which is a derived tool from ONNX that allows you to deploy ISRs on different providers. And practically, uh, we do in Vivoka, we develop our speech technologies, for example, ISRs, with PyTorch. Then we convert the model to of the format model dot ONNX, and then we have the possibilities to obtain a model from ONNX or another format. So the ONNX, why we use it? In fact, because it allows us to apply different techniques of optimization. And here we have four: pruning, fusing, tiling, and vectorization. And we will give examples for each one. So for pure pruning, in fact, is a kind of simplification or reduction of the graph that represent our models. So here, for example, we have, let's say, a normal or a non-optimized model that contains a convolutional network or a convolutional network, another and a dropout, another convolution, and thanks to pruning, we will obtain only these two layers. For fusing, the process is different because here we will merge the convolutional with the function u in only one element. And for the tiling, we will apply some mathematical optimization. Here, for example, we have multiplication task, which will be optimized through some division and mathematical optimization. So regarding the vectorization part, here we have many mathematical operations that will be optimized through a representation or a kind of vectorization. And to give you a little view of the results that we can obtain, here, for example, we trained two models that we call BERT-based BERT and Roberta. Three models: BERT, Roberta, and GPT. And as you can see, here we have the main inference speedup using PyTorch. And as you can see, by applying ONNX runtime optimization, we achieve twice or even 3 times faster. We obtain ISRs with twice or 3 times faster than the model non-optimized. Another technique that we use is called the quantization. And quantization here is a simple example for image. As you can see, for an image in the float 32, when we reduce it, thanks to quantization, we obtain this image. It still has the principle of all of the information, but in a minor quality. So it allows to go from 32 bits to 8 bits, for example. And so we can obtain a faster calculation on CPU and even 4 times lighter models. And here we have some results that we obtain by testing our models. In fact, here we have the PyTorch model. The size model, we have, for example, 267 megabyte. By applying ONNX, we reduce it a bit, but by applying ONNX quantized, we obtain 64 megabyte. So here we divided the model size by 4, while we retain the same accuracy of the model. And for the speed or the RTF or for the inference, we improve also the inference time. For PyTorch, for example, we have 15 milliseconds versus 4 milliseconds for the quantized one. So for the conclusion, so we saw a classical architecture of the ISR. Then we saw also a challenge of deploying ISR on an embedded device, and some optimization techniques that we use to solve these problems. Thank you.